Welcome to this series on computer vision and digital signal processing. In this two-step video compilation, we'll be talking about various topics related to image acquisition and modification. So in this video, we'll be talking about image breakdown, pixel density, and its effect on sharpness and detail, photo matrices and arrays, photo compression, 2D and 3D image recognition, and depth sensing in modern technology. So, we all identify this as a house. But we couldn't do this back at birth. Once we started observing multiple houses, we understood the basic framework, or in other words, the skeleton of a house. A door, a couple of windows, a roof, and so on. And now we can identify any house as such just by understanding that it possesses that basic framework. This is our idea of a typical house. Now whether you ask a toddler to draw this or perhaps an adult in a very short amount of time, this is probably what you'll see on a piece of paper. This is what I'm referring to when I talk about a framework. You have a roof, a couple of windows, and a door. Now, our objective is to make the computer understand this basic framework. This can only happen the same way that we learn. We have to create multiple images provided to the computer and tell it that this is a house, this is a house, this is not a house, so that it can identify for itself the basic framework. Let us take a look at this rather simple picture of a house. Let us start to analyze this. So it has 4 windows and no additional features, as that will start confusing the computer at the beginning. If, say, I consider this as one single grid of a photo, then we are looking at the most major color here, which is this brownish orange color, and that is all that the computer recognizes if we have a single grid. Now, let's say I divide this into a 2x2 matrix. Now, it identifies the most prominent color in each of these 4 sectors and assigns it accordingly. Now, there's no difference between the previous image and this image. But if we go further down, break it down into, let's say, a 3x3 array, we are looking at something that resembles a triangle sort of picture. While this doesn't give us an idea that it's a house, we're getting closer to what we want. Let's divide this up further into a 4x4 matrix. Now we can see 2 windows, but still you cannot identify that it's a house. If you divide it further into 5x5 matrix, you start seeing the chimney and the 4 windows, but it's still not clear, and that's the problem. We have to keep going further and further down. 5x5, this is a 6x6 matrix, and you slowly start recognizing that, okay, maybe this could be a house. If we go to a 10x10 matrix, we now see clearly that it's a house. It has a red colored roof and a chimney, and you can start working your way around this particular version of this condensed image. So that is the idea of pixels per inch, DPI, and all of these. They say how many small grids that we can analyze can be put into unit area or length. So as that value increases, you have more data to process, and hence you get sharper and better quality images. So let's take a real world scenario. We have a 3x3 matrix as before, and we say this block is of a green color. Now the values there, don't get confused by that. That's another way of notations for numbers. Now we have decimals where each number can go from 0 to 9. In the case of hexadecimal, we can go from 0 to 15 in each number. So each number has 16 sets of values. So 0 to 9 and then A through F. So the conversion has been given below. For example, if you take the value of G1, it says D2. So using the algorithm, the right side place will be represented by 0 for I. So that would be 2 for the right side. Let me get a pen outside. 2 times 16 power 0, because I equals 0 from the right side. This is zeros and this is ones. And then D, which represents 13, because 9, and then A is 10, B is 11, C is 12, and D is 13. So 13 times 16 power 1. Now normally, if you were working with decimals, instead of 16 you'll have 10. So you have 2 times 1 plus 13 times 16, which gives an equivalent decimal value of 210. So in case you're confused with this system, we are trying to assign a value between 0 and 255. So a total of 256 values are being assigned to each individual color. So we have R1 as 0F, G1 as D2, and B1 as 33. And you can convert each value accordingly. Now this is the first, this is the second block, this is the third block, this is the fourth block, and you go up till the ninth block. Now, 2D arrays aren't generally preferred by computers, so in most cases what happens is they get converted into a single matrix, and based upon the algorithm you can have different forms. For example, I've considered 2 scenarios where in the first case each set of blocks belongs to one major block here. So we have R1, G1, B1, and then R2, G2, B2, and so on up till the ninth block. Another way to look at it is to take all the reds from each block, so from the first block, from the second block, from the third block, all up till the ninth block, and then start with the greens and then with the blues. Now if you're wondering why we took just R, G, and B values, it's because these are primary colors. You can generate any color from a combination of R, G, and B. Lossy versus lossless compression. Now most images that you take come in this array format called raw images. This is just a set of data that you really can't make much out of. It's just a set of strings and numbers, and you cannot visualize that. What we tend to do is we create an image using an algorithm that is predefined to create an observable image format. So we all know JPEGs, GIFs, JPGs, PNGs, vectors. These are different forms of images. And we're going to talk about the 2 main types of compressions that happen. Now, generally, image files are very large, and it becomes practically impossible to store many of them on our modern day smartphones, laptops, which have limited amount of space. So we need to compress them, which, as we have talked before, we need to reduce the pixel density from this scenario to say this scenario, while giving an acceptable image quality. So now what we're trying to do is we will talk about lossy and lossless compression. Now in lossy compression you tend to lose a bit of the data while converting it from a higher capacity to a lower memory capacity. In lossless, you are ensured that no data is lost. So the image quality will be the same before and after, at least in theory. So an example for lossy images are JPEGs. Lossless images are GIFs, which is why when you try to zoom into a JPEG, you tend to get distorted, scratchy sort of images. Because it does not have the quality necessary for that kind of zooming. Take a vector for example. No matter how much you zoom into a vector, you always get sharp, defined lines. and that is a characteristic of lossless compression. Let's talk about 3D. Most objects we see in our day-to-day life are three-dimensional in nature. So take cars, houses, all of these cannot be visualized from just a single angle. And if you take the example of self-driving cars, you need to see a car from various angles, and it's impossible to analyze it from just one, because then the computers cannot realize that it's a car from another angle. So our objective here is to convert a 3D object into a set of 2D images. Let's take a simple 3D object. So we have a house here, and we will give the algorithm different dimensions of the house, from this angle, from this angle, from this angle, and then we zoom in, and then we tell it this is the picture of a house, and it understands it after a couple of iterations, and there is no problem in analyzing this sort of images. But this is not the case in real world scenarios. We have multiple three-dimensional objects in one frame. So let's look at that. So yeah, we have three different objects here. We have a house, a tree, and the car. Now based upon which angle you're looking at, one becomes the primary object and the others become secondary object. And from this view, you really can't see the other objects, and you can clearly define it as a house. In this view, you see three separate entities and give them equal value. From this angle, the car seems more important. From this angle, the tree seems more important. And if I zoom in, right now the tree is the most important object. So you've got to make sure that the computer analyzes an image and understands which is in the foreground, which is in the background, and which is the principal component of the image. This is what all these algorithms are about. Depth sensing. So we all see these images of phones having multiple cameras, and most of the time it doesn't make sense to us. Let us try and analyze a simple situation of what happens here. So we have a main camera and a depth camera. These are the two we're going to analyze right now. Now, let's bring these two up. Let's ignore the other cameras, because this is what happens in your portrait mode in your smartphones. So let's say the main subject, for example, if you're taking the photo of yourself, you're right here, and there is some object in the background, let's say a tree. Forgive me for my drawing skills. Now, these have different apertures and different focal lengths, both of them. So, the image sizes of both these objects will change for each camera. So for example, in the main camera, it could be that the man seems larger than the tree, and you'd have a different ratio of sizes for the depth camera. So using an algorithm, it takes the difference in sizes and says this is the approximate distance between these two due to the difference in proportion sizes for the two cameras. That is the idea of depth sensing. And to learn more about sampling, reconstruction, and all other stuff, please look out for my digital signal processing. Right now, a like, share, and a subscribe would be great.